Hi all. So today we're going to talk about this problem, 1.15, flux through a circle. So it's basically asking us to find the flux generated by a point charge Q, and it's like through this certain surface. It can be either be a disk or a spherical cap. So let's do part A first, which is a flat disk bounded by the circle. And to help you visualize the example a bit more, hopefully, I created a model on Tinkercad. So the blue sphere is sort of like the point charge, and this is the disk, the green one, and this is not to scale, and the thickness will be very very thin in the problem, but it's hard to make it very thin on Tinkercad. But I hope this helps your understanding and kind of can visualize what's going on. So we know that the expression for flux is flux equals to integral of electric field dot product dA. And just take note that A here is a vector too, because it's kind of like the area vector here. So the area vector is always perpendicular to the surface, and so it kind of points horizontally. And as for E, it can point in many directions, because it can generate electric fields in this direction, in like this direction, and this direction sort of. But we're only interested in the component of E that is horizontal to A. So like this component sort of. Like if it were this electric field, we only look at this component because it is parallel to the area vector. And that is sort of like the meaning of a dot product. So how do you do that? Well, we can first just analyze one part of it. So let's say this one, and we call it beta. And so obviously the horizontal component of this E would be E cosine beta. And so now the expression becomes phi equals to integral E cosine beta dA. And remember, this time we don't have the expression like without the sign anymore, because we're just calculating the magnitude. And also like we don't need the dot product because we already accounted for it. So now let's try to find E first. E will be quite easy actually. It'll just be phi equals to I'll write it like 1 over 4 pi epsilon naught. So this is basically K, and then Q over the distance. So the distance from Q to, let's say, the point here. So what is this distance? Let's call it R. Well, we know that based on the trigonometry here, sort of, we know R equals to L over cosine beta. So we can write like L over cosine beta squared, and then cosine beta dA. And now we need to write dA in terms of alpha or something else, because we cannot really put a bounds here or here for when we're integrating with respect to dA. So let's try it. So for a disk, how can we find the area of it? Well, we can make many rings in it, right? So let's say let's say this is sort of like a disk. So we can draw one ring in it. I can draw another. Let's just consider this ring here. So this ring is, what's the circumference of this ring? Well, it's 2 pi r. And what is this distance here? So like the sort of like the thickness. It's just dr. So we know that the area of this little piece of ring here is dA equals to 2 pi r dr. And remember, we don't need to account for the thickness of this part. So maybe some of you will be thinking like this part. So, or we can go back to the model here. We don't need to account for the area here. So like the actual thickness of it, because the problem assumes it to be very thin. And so basically now we have dA equals to 2 pi r dr. Yeah. Actually, let's call it another name because we already have r. So like remember r is this distance. But for this one we need another name. Let's call it B. So the area is 2 pi b dB. And what is b? So we can do it with trigonometry again. We know tangent beta equals to b over L. And so b equals to L tangent beta. And so we know that dA equals to 2 pi b L tangent, it should be 2 pi L tangent beta, and then d L tangent beta. And since L is a constant here, we can also write it again like this. 2 pi L squared, so we pull the L out of that d. So it's 2 pi L squared tan beta d tan beta. And what is this equals to? Well, we know that the derivative of tangent is secant squared, which is equals to 1 over cosine squared x. So we can basically write it like this here. So 2 pi L squared tan beta, and then we can write here secant squared alpha, secant squared beta, and then d beta. And then dA equals to, let's try to simplify this a bit. So sine beta over cosine beta, cosine squared beta over 1 d beta. So this becomes 2 pi L squared sine beta over cosine cubed beta d beta equals to dA. So now we have this expression. So let's plug it back into this expression here. So I'll write it here. So phi equals to integral of 4 pi epsilon naught, 1 over that, q. Let's actually just write it q L squared. Let's do q cosine squared beta over L squared times, and since it's times cosine beta, we can basically write it here as times cosine cubed. And then dA, which is 2 pi L squared times sine beta cosine cubed beta d beta. And so we can basically cancel out cosine cubed beta and also L squared and also 2 pi, so we have 2 left here. So phi equals to integral of q over 2 epsilon naught times sine beta d beta. And since this is a constant here, we can pull it out. And remember our bounds. What can we put it as? Well, we should do from 0 to theta. Because it's basically from 0 up until theta. And then since we are rotating it, so sort of imagine like we're rotating it, that's why we don't need the lower half. So it's just phi equals to q 2 epsilon naught and then negative cosine beta, and then where beta equals to 0 and beta equals to theta. And so phi becomes q over 2 epsilon naught 1 minus cosine theta. And so that is the phi we found for part A. Now let's try part B. Part B is asking us to find the flux through a spherical cap. And let's visualize this again using Tinkercad. So this is sort of like a spherical cap. It shouldn't be a hemisphere, but just for the sake of simplicity, I just modeled it as a hemisphere in Tinkercad. But really just should be a portion of the sphere, a spherical shell. And so we're trying to find the flux through this spherical cap. So let's first find the electric field first. So because it is a spherical cap, we can create a Gaussian surface, a sphere, that encapsulates this cap and has Q in the center. And so the radius of this sphere should be R, not L though. Because remember, L is just the distance from Q to the disk, to the circle here. Remember, like, the problem talks about how there's a circle and we create the spherical cap so that it covers the circle completely. And so L is just we define it as the distance from Q to the circle here. But actually R should be the radius because it's directly connected to this point, which is also on the spherical cap. So let's write down the formula first. So the surface area should be 4 pi r squared for a sphere. Q enclosed should be small q over epsilon naught. E equals to q over 4 pi r squared epsilon naught. And so now let's recall. So the definition of phi should be integral of E dot product dA. But in this case, we don't really need to worry about the dot product because, well, every electric field out of the surface is perpendicular to the surface. So in other words, the electric field vector is always parallel to the area vector. And so we can just write it as E dA. And so now our only task is to find dA, the surface area of the spherical cap. And so to find the surface area of the spherical cap, we can slice it up into rings. So like into different rings. So again, let's visualize this. So let's say I have a ring here. If we add up these rings, then we will find the surface area of the spherical shell. So how do you find the surface area of this ring? Well, the circumference is 2 pi b. And so we call this one b. So just to make it clear, this is b. We define it as. And the circumference times the thickness here, which should be r d theta. So if you refer to this diagram here, so this is r, and if we move it by d theta, so this is d theta, so this little bit here, and so then this little thickness here should be r d theta. So dA equals to 2 pi b r d theta. And what is b? Using trigonometry, we find that b should be r sine theta. So dA equals to 2 pi r squared sine theta d theta. And so phi, let's write phi. Phi should be integral q 4 pi r squared epsilon naught times 2 pi r squared sine theta d theta. And just remember, we're also integrating from 0 to theta with the aforementioned reason in part A previously. And so let's simplify this a bit. So r squared cancels, this cancels to be 2. And so again, we have this q 2 epsilon naught 0 to theta sine theta d theta, which is equal to q 2 epsilon naught 1 minus cosine theta, which is the same as the result we obtained for the disk.